I'm Bob McGuire, N4HY. I'm the Chief Scientist at the Hume Center at Virginia Tech, and I'm a member of the Electrical and Computer Engineering Department and Aerospace and Ocean Engineering Department. A little over a year ago, almost 2 years ago now, we began a project called Phase 4B, which is a mission to put a geostationary payload on board someone else's satellite, so it's much less expensive to get on orbit. So all we have to do is build the electronics and the software, and the other spacecraft people give us power supply and a ride to orbit. So doing this takes a lot of work. Even though we're not doing the whole spacecraft, we're only doing a piece of it. It's a lot of work. So the original mission was to provide emergency communications for radio amateurs, capabilities rather, for radio amateurs, so they could help in national and state and local emergencies. But that's no longer sufficient. The reason is that we want to remain relevant for many years going forward, because we are going to build an entity, a spacecraft payload that will work for many years. And we know that communication systems to do emergency communications with digital voice, digital data, and using spacecraft and other things are coming online very quickly. So emergency communications will be a part of this, but it will not be the only thing. We also need to be able to do technological experiments, educational experiments, put amateur radio in space, and do things like help put a lot of users into the 5 gigahertz and 10 gigahertz bands in order that we may preserve our ability to use those bands for amateur radio in the future. I've been very fortunate here at Virginia Tech to have many terrific people working with me to help me, because this is not something I can do all by myself. I need a lot of people to help. We have spacecraft people, space people, mechanical people, thermal people, computer people, RF people. We have all sorts of people at Virginia Tech that help make me look better. And one of my favorites is one of my first students at Virginia Tech was Zach Leffke, who is KJ4QLP. Zach designed a small ground terminal using low power equipment, inexpensive receivers, and inexpensive antennas intended to provide a distributed receiver ground station system for his master's thesis. Zach has been a part of the geostationary Phase 4B program since its inception, and I'm going to let Zach tell you a lot of the work he's been doing, including getting us some toys to play with.
All right, thank you for the intro, Bob. We're going to kind of go over our prototype system that we have here. It's kind of a version 1 development system for the Phase 4B mission. So in order to design the transponder, we want this to be relevant, right? 5 gigahertz up, 10 gigahertz down. So we want to have a transponder system that is representative of that, as well as a ground station side that we can do the development of all the waveforms that we need for this. So we're going to start kind of over here. Everything I've designed here is kind of built into ammo cans. We're using GNU Radio as
You must have been a Marine.
Yeah. Yes, I'm familiar with these, and I know a lot of hams like ammo cans too. So inside here is our transponder simulator. We have a USRP from Edis Research, a B200, that's acting as the software-defined radio, an Odroid XU4 from Hardkernel, which is a single-board computer that's the actual processing unit for it. And then kind of underneath all of this down here is the 10 gigahertz upconverter. So we have an L-band IF coming out into our 10 gig upconverter from Kuhn Electronics, and then out the Kent Britton's Vivaldi antenna design here. So that's our satellite downlink side. And then similarly, we have a 5 gigahertz uplink. The USRP can work all the way up to 6 gigs. So we don't need any upconverters or downconverters to cover the 5.6-ish gigahertz uplink.
Have you decided to put a low noise amplifier in here yet, or right now?
No.
Okay.
The intent of all of this is tabletop development, kind of across the room, maybe.
Mm-hmm.
So for this first version, no, it's just the simplified version here, and we'll get to why, one of the reasons why we're doing that here in a minute when I go over the ground station. One other thing that we have in here is needed is a 10 megahertz reference. In this case, it's a lab grade OCXO, which you'll see kind of repeated throughout the ground stations when we go through that. But that's to provide a disciplined 10 megahertz reference to both the software radio as well as the upconverter. so that we can kind of have confidence in the center frequencies of this equipment. So this is just, again, for development. The important thing, the final target device, I'm not even going to take it out of the static bag because this is the only one we have right now, is the Astra SDR from Rincon Research Corporation. So you can kind of imagine, and of course the stickers are blocking it from view, but this is our one of the first versions that came from Rincon that we'll be doing the final sort of development. This is the target device. This is a space-rated, software-defined radio. And it will replace.
I'm trying to get a peek at it behind the glare on the package.
The glare, yeah.
So you can see there's an actual circuit board in there.
Yeah, there's a kind of CubeSat form factor software-defined radio in there.
It has a Zinc 7045 on it, and an analog devices RFIC, and we are going to put all sorts of new radio software on it using what's called RF knock, which allows us to do interesting things with the FPGA that's part of the Zinc.
Right, so you can kind of imagine this single board with its massive FPGA resources and the RFIC replacing kind of the entire USRP and the embedded computer here. Again, this is just for kind of simple get up and running development, and then eventually we'll target this device.
But I mean, it's really very illustrative, Zach. I'm glad you brought that out because all of that is replaced by that, with the exception of the power supply and antennas.
Right. And
so
the
these
we need an up converter.
We need an up converter for this, and we probably won't use Kuna because it's not space rated, but we'll use something to be an up converter. And then the antennas will be on outside of the spacecraft. Consider the box the spacecraft, so these antennas are on the outside like they would be on a spacecraft.
Right. And there's some nifty switches and ports on the back. But actually, we'll go over that with the ground station because that's the one I think is a little more interesting. So we'll go ahead and box this guy back up. So again, we have our 10 gig outlink here, or downlink here, and our 5 gigahertz uplink here, so receive side. And then we'll move over here to the ground station side and take a peek in it. Actually, let's start with the connectors on the back. So first of all, it's all running off of 12 volt DC. This device I think is interesting because minus the power amplifier that you need for the uplink, this could actually be an example of a DIY or a kind of roll your own ground station for the Phase 4B mission. It has everything you would need, and it's actually kind of close to the price point that we're targeting with this too, which is about $1,000 for a complete system. It's in this version it's a little bit higher because it's one of the prototypes and it's in development, but it has some of the representative parts that you would need to do a roll your own ground station for Phase 4B. So again, hams like, not all hams, but a lot of hams like power pole. So I went with power pole for this. We have our main power supply here, and then we have a polarization select option here, which I'll get to when I talk about the LNB. The USRP bypass is just if we, instead of using the embedded computer, if we want to talk direct to the USRP with like a laptop or a more powerful processing system, then we can, but it's not really needed. And the COM port is just a serial connection into the computer so that you can log in over UART if you need to reprogram something.
What's that cable?
This cable?
No, the other one. Is that Ethernet?
And then finally we have Ethernet. Okay. And so this is actually how you can kind of imagine the final system working, at least in my mind, how I would imagine it working. All of the processing, all of the SDR operations that we need are done in the box, and then we have an Ethernet output that would plug into a laptop that's running kind of the GUI features. And maybe it's a web server running on the computer that's your interface, maybe it's some other application that's running. But kind of the hardcore processing is done in the box, hardcore signal processing is done in the box, and then the kind of higher layer or higher level interfaces are going to run on the computer. So for today's demo, we're just doing a simple tone demonstration to show a transmit and receive capability here. But let's go, before we get to that, let's peek in the box and go over the last little bits. So very similar to the transponder design. Again, we have an Odroid XU4. We have a B200 from Edis Research. Instead of the 10 gigahertz up converter, we have our bias T. That's this mini circuits part right here. And then again, we have this 10 meg reference down at the bottom. And then in this case, finally a splitter that sends the 10 megahertz both to the as an injection into the bias T to send 10 megs out to the dish if you need it. And then 10 megahertz again to discipline the user. And I'll come back to the 10 megahertz thing here in a minute as part of the reference.
You're going to need to tell us why we have 10 megahertz going to the dish.
Right. In this case, we'll get to that here in a minute. So that's it in a nutshell. You have a small embedded computer. It looks like a Raspberry Pi, but it's actually much more capable than a Raspberry Pi. A Raspberry Pi is probably not sufficient kind of compute power for the kinds of things we want to do on Phase 4B. The Odroid XU4 has more RAM, faster clock speeds, more processors, all that kind of stuff. So we think it's maybe kind of a lower end of what's necessary for.
So as I recall, the XU4 has 8 cores,
Yes.
but they're 4 cores of one type and 4 cores of
Yes.
another type. So you have to figure out how to do what's called processor affinity for the right tasks on the right processor.
Right.
So though it's more capable, it still requires a subject matter expert in computer software to figure out how to do all
Right,
that.
and the target there is to have the bigger cores, the more capable cores, kind of running the signal processing piece, whereas the other cores are more for like running the web server, kind of housekeeping features that
Sure.
don't require as much compute power.
Great.
And then, of course, you need to have your dish and your low noise.
Wow,
block
look at
here.
that.
So this is actually, much of this came directly from conversations had with Tom Clark, K3IO, when he presented for AMSAT, not this last symposium, but in the, that was 2016, in the 2015 AMSAT symposium, he presented a paper where he had a block diagram of a notional Phase 4B ground station. This is kind of the implementation of his block diagram. And it includes things like the collapsible dish that you can buy on Amazon. This LNB, this is one of my favorite discoveries of working on this project. I've heard stories of it, and now I know it's true. This LNB is about a $7 part, ordered on Amazon, and it's effectively a 10 gigahertz down converter. And it does work, and you'll see that demonstration here. I know a lot of hams in the EME world, microwave world, they love using these as kind of cheap, get-on-the-air 10 meg down converters, or 10 gigahertz down converters. And it does work.
And it down converts to what?
So in this case, I have the numbers. I'm glad I wrote these down. The
Zach and his meticulous notes.
Yes. So the local oscillator is, so this, to be specific, if anybody's thinking about buying one of these, this is a universal KU band LNB. And the universal part is important. It's kind of a European frequency allocation. But you need that in order to have the right kind of lower local oscillator frequency to make it work properly with 10 gigs. So in this case, the IF range, in order to receive the amateur satellite service 10 gigahertz allocation with this, the output frequency is between 700 and 750 megahertz. The design center frequency for this guy is around 900 megahertz. It's an L-band, 900 megahertz and kind of up. It's a L-band IF. But
So if I
because the
move it
filters-
down 200 megahertz, does it degrade the performance?
I'm sure it does to some extent, but the filters, again, it's a $7 part,
Yeah.
so they don't have super tight filters in there. They don't have even the oscillator, which you'll see.
So for experimentation, it's more than enough.
It's perfect.
Great.
You'll
Okay.
see we have plenty of receive capability with this, even
Terrific.
without the dish. We have the dish set up here to show the kind of full setup you would need. But even without the dish, actually, you can see in the second ground station that we've developed here, this is kind of how we're going to do the tabletop development. Just mount the LNB, point it at the transponder,
Oh, neat.
and that's kind of all you need. And even for 5 gigs, in this case, we just have a whip on this guy instead of the log periodic. So that's your sort of tabletop development demo version. But when you want to get on the air, just put this guy out in front of a dish, and you're still good to go. And again, the one thing we don't have in this development setup is the 5 gigahertz PA. Total price for this entire package, including the dish, including the LNB, is around $2,000, which is about 3 dB higher than the target price point for Phase 4B.
And the biggest piece is the usurp?
Biggest piece is the usurp. The other biggest piece in here is something that John Q. Ham probably doesn't need to buy. And that's our laboratory grade OCXO.
Right.
So getting back to that, again, talking about the cheap nature of the LNB and the expensive OCXO in there, it's about a $700 reference oscillator in there for the 10 megahertz. The reason we did that is we actually have a family of LNBs that we want to kind of characterize and see what is their frequency stability, how good are they, how off are they in the downlink frequency. And so we wanted to have a stable reference in here in order to do that. The average ham actually doesn't need a 10 meg reference that good, right? In fact, there's conceivably designs where you don't even need a reference at all. You will be off in frequency, but because you're using an SDR, you can compensate for that and use, if you have a known signal that you're looking for, you can use that to determine what your frequency offset is and then tune in software for that to automatically compensate. So in this case, though, we wanted to have it so that we have a good, solid, kind of stable reference. in order to characterize the different types of LMBs out there, maybe come up with recommendations. You know, this one's super stable, this one's all over the map, that kind of thing. It's about $700 for the USRP, about $200 for the computer, with all of the accessories, including the jumper cables and all of that. The mini circuits components, of which you need the bias T for sure, is maybe $20 or $30 for the simple ones you would need. Which actually brings us to another point. So these LMBs have two polarization schemes that you can use. They have a vertical and horizontal. And so what we've done back here, that's just controlled by the bias voltage. So all I have in there is a little voltage regulator that outputs. One of them is the direct 12 volts from the supply, and the other one is a little step up regulator that puts out about 18 volts that switches between horizontal. So I can flip and go, I want horizontal, I want vertical. And
all right, Zach.
It.
Zach, we have about 9 minutes left on my SDHC card, so let's do a demo.
All right, let me get this guy back up. Hopefully nobody saw my password there.
No, I hope not. I'll see if I can.
Change it after the video.
I think you should, or I'll try to blur it out.
I talked so long that my screen froze up. All right, so what we've got going on here is actually, you know what? To give you the full effect, I'm going to shut these down and restart them. So on the left, I've got SSH access into the computer on the ground station, and you can see I've actually named it P4B GS1. That's Phase 4B Ground Station 1 for the host name, and then over here we have P4B Transponder. And so all I'm using here are tools that come with GNU Radio. So I've got GNU Radio installed on these embedded computers. It's the framework we're using for development. And when you install GNU Radio, more specifically UHD, which is the drivers for the USRPs, they come with some utilities. So one of them that we're going to use is UHD FFT, which just gives you a kind of a simple spectrum analyzer type display.
Yeah.
So we'll use that on the ground station side to look at the 10 gig downlink. And then on the transponder side, we have UHD SIGGEN, which is just a simple tone generator. So I've worked out the kind of IF frequencies that I need for these. So I'm actually tuning my SDRs both on the uplink and the downlink, or on the transmit side and the receive side to the IF frequencies and not the on-air frequencies. But again, it's using that 10 gig up converter, so we'll get these fired up. And so this is running over X window forwarding, SSH X window forwarding. So let me change this. So you can already tell, right now we're looking at 1 megahertz of spectrum, and I don't see anything, right? There should be a tone. Where's the tone? Let me widen this up to 2 megahertz. There we go. Now we see a tone. And if we come back over here to the transmit side and do some fine tuning here, you can see that as I increase the frequency here, our tone on the receive side is sliding. And you actually see this guy is showing on Phase 4B Ground Station 1, and then the transmit side is Phase 4B Transponder. So I actually know that it's about 500 kilohertz that we need to correct. And the reason for this is actually not on the transmit side. I'm compensating on the transmit side just because it's easy with these sliders. But actually the offset is because of the LNB. So the specification sheet for that particular model of LNB says plus or minus 1 megahertz of stability. So we're at about 500 kilohertz low on that side.
Well, that's not ridiculous because it's easy to compensate for.
Exactly. So this is the kind of characterization that I was talking about. I can trust that number because I know that my 10 megahertz references are laboratory grade and stable. That's about it. And just to prove that it's true, I mean, you saw me tune. I can do things like change the transmit gain here. So you can see as I drop the power level on the transmit side, it decreases. Again, this is just kind of a simple tone demonstration, but it shows kind of the beginnings of what we're going to use for the full development and kind of the end target goal of what you would need to build your own ground station for Phase 4B. And that's about it.
Okay. Zach, if you'll take this, let me
Sure.
wrap this up.
Okay, so you saw Zach has put together some neat hardware for us to play with. So we are now generating tones. Well, a tone doesn't carry much information. So what do we have to do from here? We have to write some software. So at the symposium 2 times ago in 2014, we demonstrated a polyphase filter bank structured receiver where we took in 4 channels at 4 different frequencies, and we sent them all down faster on 1 frequency. So that's kind of the overall structure. We're going to listen on 4 channels and send it out faster on 1 channel so that all 4 channels get their data down. So we're going to try to do this in a great big way going forward, because in the Astro SDR, which is the little CubeSat shaped board that Zach showed you inside the protective envelope, we can do many channels in parallel. How many? Well, we have to characterize that. Let me explain that to you. The spacecraft we ride on will give us an antenna. How big is the antenna? How much gain does it have? Are we able to point the antenna when we need to point it at a place on the Earth? Those things determine how much gain we will have in our system, and how the noise floor will look, how much transmit power the station on the ground will need in order to get into it. So all of these things go into a thing called a link budget analysis. The link budget means how strong will the signal be if I transmit with so much power, and how much data can I get through when I transmit with that power. All of these calculations are to be determined. Why are they to be determined? Because I don't know the limits that the spacecraft owner will put on me as of now. In other words, these are all things that a spacecraft system engineer will be doing in the future. But these devices, we hope to be able to have multiple people play with. We will let the design be known. We will allow some people to work on these locally, and then have other people work with us on these. I'm hoping that in the next few months we can put them outside. Near to Virginia Tech is a place that I can see with my eye from on top of the building we are in, which is the Hume Center in the Corporate Research Center near Virginia Tech. I can see Poor Mountain from the top of this building. And on Poor Mountain, there are many transmit towers for TV and radio stations. First, can I put my RF equipment up there and it work at all, given there's several 100 kilowatt transmitters up there? But if I can put it up there, this is a terrific place to see the entire area around here for people to work on. If that doesn't work, the Virginia Tech Amateur Radio Association has a place on top of Brush Mountain where it has its repeater. And there we have a tower. We can climb up the tower and put 10 and 5 gigahertz omnidirectional stuff, or even directional antennas up there to experiment with. Southwest Virginia is lots of mountains, and Virginia Tech is right in the middle of them. So we'll be able to do some experiments here locally, and that will be reported on in the next few months. Zach, I want to thank you for your help, and I hope all of you learned something from this, and we will be doing more of these YouTube videos in the future as this becomes more mature and available for others to use. Thank you, and I hope you enjoy it.